All right. Okay, we'll go ahead and get started. It's week 6, Wednesday. No lecture on Friday in observance of Veterans Day. Do we have any veterans in our class? Anybody? Anybody have service? Okay. Well, sometimes that we want to express our gratitude to our veterans. So yeah, no lecture on Friday. We'll be back on Monday. But anyway, today's lecture, I wanted to cover a little bit more on kind of data visualization and kind of visual exploration. We introduced Matplotlib on Monday, and please kind of work through that lecture, those notes, and I do highly encourage you to test out and explore the plot features within pandas. So again, when you have a pandas data frame and you call plot on that data frame, it'll take your index and generally put it along the x-axis, and there's different kind of plots that you can create, and you should explore that. We will take a look today at visual exploration with Seaborn. And so Seaborn you can think of Seaborn as kind of almost like little templates for Matplotlib. So there's a lot of plots that you can create with Matplotlib, and there's some handy, nice little plots that you might frequently use. And Seaborn uses Matplotlib and kind of creates a set of plots and visualizations that are quite convenient and handy. So we'll import our packages as usual, and Seaborn will get imported using SNS. Okay. There's a few tutorials and some references that I will refer to you guys. Okay, so this is overview of Seaborn plotting functions, and you have kind of these different things. So this is the histogram plot, and this is kernel density estimation, where they kind of stack these things on top of each other. More on some of these different, this is for the distribution plot, a little bit more specifications on exactly what needs to be done. So this is kind of your standard looking histogram. You can kind of do a kernel density estimation to get kind of the smoothed out curve, and then this would be the empirical CDF. So I'm not 100% how familiar you are with some of these different statistical concepts, because as far as this class goes, you only need like stats 10. So I don't know if you've taken, say, 100A or 100B already or not yet, or maybe that's coming or not. So these are different kinds of distribution plots that are handy and relevant and frequently appear in different statistical contexts. That's not it's outside the scope of this course, right? So I'm not going to be going into the use cases for all of those things, but they are, those are frequently used plots and tools, and we have the tools to make these plots here. Okay, I'm going to load up a data set called Penguins. This is there's a Penguins data set. I guess people went to Antarctica. And they went to these different islands in Antarctica. So what is this? The Torgerson Island. Let me just kind of show you. So, look, you can go to Bing Maps. Okay, so here is. All right. Oh, okay. Mercator projection, not the greatest projection for maps, but okay. So you go to Antarctica, and there's like islands, and penguins live live in Antarctica. Anyway, so we have this, and there's different species of penguins. We have Adelie penguin. Oh, I know I don't want to go to maps for that. All right, show me some pictures. Okay, so these are your Adelie penguins. And then other species of penguins we have. Oh, how do we? Oh, man. Species. Now I'm okay, so we have Gen 2 or Gentoo, I don't know how to pronounce. Okay, so these are other penguin species, and then I think another one in the data set are the chinstrap penguins, which look like this. Okay, so anyway, so there's three species of penguins. The researchers kind of found them on different islands, Torgerson Island, Biscoe Island, etc. And then they measured things like the bill length, bill depth, and flipper length, body mass in grams, and the sex of the penguins. And the original research, they were looking at what you call sexual dimorphism. Basically, so in some species, like male and female, like it's very difficult to distinguish between the two, or like, you know, they're the same size and things like that. And only if you look very carefully at, say, like, you know, reproductive organs can you tell the difference. But then other species, kind of like lions, for example, they end up looking different, right? Like an adult male lion and an adult female lion look very different and things like that. And so the researchers were kind of interested to see if this, you know, is there a difference between male and female penguins and stuff. And they looked at different species, and they measured things like, you know, are there differences in the length of the bill and the depth of the bill and things like that. And so they gathered this data set. But anyway, this data set's a nice data set, and we don't have to necessarily look at the same question that the researchers were looking at, but we can just say like, oh, what's the difference between some of these penguin species and stuff like that. Okay, so anyway, let's take a look. So the first thing is there's something called the distribution plot. And this is kind of Seaborn's way of doing like histograms. So kind of the default is to kind of create a histogram. And so Seaborn is built on top of Matplotlib. So you call a Seaborn function like sns.distplot, distribution plot, and then you end up calling PLT from Matplotlib, because basically Seaborn creates kind of a plot in Matplotlib, and then ultimately to show it, he'll call plt.show. So Seaborn's kind of like these prearranged little scripts or tutorial templates for producing things. So here we're going to say, you know, let's look at the penguins data set, and let's put flipper length measured in millimeters on the x-axis. And there you go. You get a histogram for flipper length. And that's kind of your default things. You can change a few things. You can change the number of bins, and you can also add something called a rug plot. And basically a rug plot is handy when you want to see like individual measurements and values. And it's a little bit hard to see because you have blue on top of blue here. But you can see, you know, for example, you know, this bin represents, say, you know, three values, you know, 179, 180, 181, or something like that. And you can see the kind of the individual units. One thing, a rug plot works best if you don't have discrete values, like if you have continuous values and you want to plug it, plot say 190.2 and 191.3, and all of those would show up as kind of individual little, almost like little hairs, to kind of display, and so kind of seeing like how many of these tiny little individual hairs show up in a region, you get a sense of how the density of points in that small range. So anyway, here I've changed to the number of bins. I said rug equals true to add a rug thing. Bin width, you can also, rather than just specifying the number of bins, you can specify how wide each of the bins should be. And so here, each bin, it has a width of 2. Two unique values show up there. You can also specify where the cut points should be for a bin. So these are all just different, like if you really want to customize what your histogram looks like, okay? And so here, and notice here when I specified where the bins are, I just kind of specified cut points, and I didn't even span the entire data set, right? The entire data set goes up to 233 or something like that, 232, and I just said ended at 200, and this gives me just kind of that portion, which would be very misleading if I didn't tell you that, like, I left off a whole bunch of data here, okay? You can do KDE equals true, and this will add a kernel density estimate, basically a smoothed out line on top of the distribution plot, right? And again, you can combine a lot of these different options and features. So if you want to specify more bins or smaller bin width or whatever you want, you kind of get that, right? So this is just kind of your smoothed out thing. You can change the kind of the plot itself. So the default kind is the histograms that we've been seeing, but you can also change it. And you can say, I just want the kernel density estimate, okay? And it plots that right here. You can say, I want an empirical CDF, and an empirical CDF, what it measures is the proportion of values that are below a certain X measurement here, okay? So at the very end, the largest value we have is 232, I think. And we say, what proportion of values are less than 232? All 100%, the proportion of values that are less than 232 is 1. Over here, the smallest value I have is like 170. So if I go down, or 171. And so if I say, what proportion of values are below 170, the proportion is 0. And then, say at like 190, what proportion of values are less than 190? It looks like maybe 23% of values are less than 190. And it looks like there's quite a few who have that have a measurement of like 190 exactly, or 191. And we said, what proportion of values are below 191? And that jumps up to say like 31% or something like that, okay? And so that's what we see, and we kind of get a sense of the distribution there. And so, and indeed, it looks like there's quite a few values, in that 190 range. So that corresponds to kind of a jump in our empirical CDF. We can also create these bivariate plots. We can look, so if we just kind of look at the first few rows of our penguins data set, we can see we got different numeric values: bill length, bill depth, flipper length, and body mass. There's actually an illustration of what is meant. Okay, so this is penguins data, and there's an illustration of what. Okay, so here are, look at that cute little picture of our 3 different species, and nope, this is not the picture I want. Palmer penguins data. And where are our pictures here? Here's the illustration. So bill length is how long this part and the build depth is that portion of the thing. And I guess there's the official name is the Coleman length, but they just to kind of, I don't know anything about birds, but apparently that's the formal name, but we'll just call it bill length. Okay, all right. But anyway, we can look at flipper length, which is their little flippers, their arms. I don't know, they're not wings because they don't fly, but they go flying in the water. All right, so here we go, flipper length, bill length, and this is kind of our distribution plot. And so by default, if you give it two numeric variables, it's going to kind of produce this two-dimensional distribution plot. You can also do, rather than having this where, the darkness of the square or the little cell represents kind of the density there, you can also have a kernel density estimate, okay? And the kernel density estimate here kind of shows you like a contour plot, right? So hopefully I don't know if we're familiar with kind of like contour plots on a map where these rings represent places of kind of equal elevation. And so as you have kind of tightly bound rings, that kind of indicates like steep elevation changes. And so that would be places where like you have kind of peaks and mountains. And so we have kind of like 3 different peaks here. And these correspond to kind of the 3 regions here that are a little bit darker than the rest of the plot. Okay, you can also, in terms of this, you can do a rug plot here, and it kind of does rug plots on the X and Y axes. Okay, and you can see kind of the density of points, and we can see, yeah, we got quite a few bill lengths between, say, 35 and 50, and we have a few bill lengths that are kind of out here. Yeah, question?
Professor, can you explain why it's like in the form of a contour map when you use the KDE?
Yeah, KDE is kernel density estimation. And so kernel density estimation is kind of the idea of, can I get like this smooth curve to represent the thing? And so for a one-dimensional thing, it basically looks kind of like a density, a PDF is effectively what it ends up looking like. In 2 dimensions, the PDF of a 2-dimensional thing is a surface. Okay, it'd be like a 3D surface, and so the way we would plot, like, if we could plot it as a surface, we could, but the default is to kind of represent a 3-dimensional surface. The default method here for representing a 3-dimensional surface is drawing this contour plot to kind of indicate like areas of higher elevation and lower elevation. So that's just how it chooses to represent this 3-dimensional surface, where basically your 3 dimensions are your 2 x variables, flipper length and bill length, and then the 3rd dimension would be the density, the height of the density area. High areas have high density, lower areas have low density, something like that. So that's just how it chooses to represent. Okay. Here along the x-axis, so now I'm just going to do a univariate distribution plot. I have one numeric variable, flipper length. Okay, so we're just going to do a plot here, and I'm going to color my distribution plot using hue equals species. So we're going to have basically 3 different colors, 1 for each species. So I do kind equals KDE, and this is what we get, and we get kind of a it looks fairly normal for our 3 different species. We have for Adelie penguins, this is kind of centered here. For chinstrap penguins, it's centered here, and for Gen 2 penguins, it's centered there. So we get basically these 3 distributions, 1 for each species here. So that's that. We can do a joint plot for two numeric variables, okay, and that's going to do basically a scatter plot with histograms along each side. Okay, so if you look at this distribution plot for two numeric variables, flipper length and bill length, and you look at this joint plot, okay, which is basically the scatter plot, you can see that, yeah, you know, if we had to draw like a kernel density estimate, there is like a good amount of kind of, we can see how this and this kind of correspond to each other, right? The density of points here correspond to kind of the peak right here, you know, which corresponds to the darker region here, okay? Which is what we have here. Looking at flipper length, if we were to just kind of go, if I weren't to separate it on the different colors here, we would end up getting the original flipper length bivariate distribution here, which is what we have here. And that's effectively what we have here. This is just like a flattened out version, just kind of compressed down for flipper length, right? And similarly, we have it for bill length. And so this is the joint plot. This is all done using Matplotlib. On Monday, I showed you a few examples of Matplotlib, and I said, you know, you could use, what was it called? Not subplots, GridSpec, okay? GridSpec was this thing where if you wanted to create subplots that were of different sizes. And basically, this is done using GridSpec. And we could see, if you remember like just the commands that we had to write for GridSpec using Matplotlib, it would be a huge pain to have to like manually write all of the things out to get the histogram and have the axes of the histogram align with the scatter plot here and here. It would be a huge pain. And so, you know, Seaborn is basically a template for something, and I think this is a fairly, maybe not super common, but it's not unreasonable to like imagine a plot that looks like this and want to kind of produce it, and to have to do this manually using Matplotlib would be a huge kind of chore. And so Seaborn makes this a lot easier for us by kind of having this nice little thing, joint plot, to do it, okay? You can also color the dots by species. And so I'm going to do the exact same call, but I'm going to add this command, hue equals species, and we get this. And so now my dots get colored by species, and then the kind of the histogram gets turned into basically little kernel density estimates, and we get you know, this thing here, all right, which is basically this thing just kind of shortened down to fit as well, all right? And now we really see kind of the clustered nature of our data, and we can see, yes, the flipper length and bill length is quite different. You know, we have these three distinct clusters for our three different species. Although, you know, individually, if you could have, you know, a penguin with, say, a flipper length of, I don't know, 205 and a bill length of 42, and, you know, kind of right in the middle. And it could be either, you know, an Adelie penguin that with really long flippers and long bill, or a Gen 2 penguin with short flippers and short bill. And it's, you know, a little ambiguous, right? Kind of like, you know, if you imagine, you know, trying to classify, you know, try to guess the gender of somebody based off of their height or something. It could be like, you know, this is a person, you know, on the taller side or shorter side of, you know, whatever. It'd be kind of difficult to do. Similarly, same kind of challenge here based on penguin stuff. Okay, here you can also do kind equals KDE, and rather than having the dots here, you would end up getting this. Okay, and so kind of looking at each species, it kind of creates a density plot, trying to create like the contours of each species there. Okay, let me go ahead and give you your first view quiz answer. Bless you. I think, hold on. let me just look up and make sure I'm giving you the right answer. Wednesday, week 6 Wednesday, our first answer is A. A as in apple. I'll go ahead and type that in here. Okay, we'll take a look at the iris data. Iris data, similar kind of to the penguins data, except we have flowers, iris flowers, and we measured things like the sepals and the petals. And we can kind of create a plot showing, what's sepal length and sepal width and things like that. So a pair plot will kind of take all of your numeric variables and just kind of plot them against each other. And this one and this one, these are kind of just kind of transposes of each other, or what inverse, where you just flip what's x and y, and so you can kind of see this and this. These are like flipped along the line y equals x. Okay, and then similarly you could specify to color the dots using one of the categorical variables. So there is a categorical variable in the iris data set, which is the species. There's 3 species: Setosa, Virginica, Versicolor, and we say, hey, go ahead and make a plot where you colored the dots using the different species, and it does so. It takes a few seconds to do it, and we can see, all right, we got 3 species, and it colors the dots. And again, much like the penguins, we can distinguish and identify the different species based on their measurements. And as far as petal width, in that location, it just gives you the individual kind of kernel density estimate for each of these things. Okay, here is there's another data set. This is the TIPS data set, and so I don't know when this data set was made, but these are like these are prices from, I don't know, must have been like the 90s or something, because it'd be like the total bill was $17 and the tip was $1.01. Okay, so they paid $18 on the $17 bill. The sex here is the I don't remember. Is it the sex of the patron or the sex of the server? Okay, and then I think, was the patron a smoker or not? So this was back when they had smoking sections in the restaurant. Okay, what day of the week was it? What time, was it dinner or lunch? And then what was the size of the party? So basically 2 people ate for $18 here, which is hard to, and here, what, 3 people ate for $12? Man, I don't even know what happened there. Okay. You can't even get a Big Mac meal for $12 after tax, right? It's like, okay, anyway. So old data set, it's just, sometimes as we go through these things, we have these historical, at this point, historical data, and it just gives you a glimpse of what things are like. Okay, here's a little bit of information. Okay. Information about the TIPS data set. We have a total of 244 entries. So we have something called the strip plot, okay? And this will just, here we're looking at one variable being the day which we record the data, Thursday, Friday, Saturday, or Sunday, the total bill, and we get kind of this dot plot. Now this is difficult to read because all the dots get stacked on top of each other. So we can jitter this, and we can do jitter equals true, and this gives us, this kind of adds a little bit of jitter here, so we can see, oh yeah, there's quite a few dots here. I mean, we knew there were quite a few dots here, but because they were all just stacked on top of each other, it was really difficult to kind of distinguish, and so we can see this. And interestingly enough, there were more people eating on Thursday than there were on Friday, but this is what we have here, okay? You can do a swarm plot, which with the jitter, there's still some overlap. It gives you a sense of the density. The swarm plot basically says, I don't like when anything overlaps. So it just kind of says, we're going to make sure every dot doesn't overlap with any other dot. And it still kind of tries to get this compression, tightly pack them together, but it also gives you a sense of how the values differ from one another as well. Okay, you can also specify color the dots using a categorical variable. And so here I'm going to do hue equals sex, which was, I think whether the server was male or female, I think. And so we see this, and it's basically the same thing, but we just added colors to the dots. Here we could, I could do hue equals day, and on the x-axis, I can do sex. So right now I have the categorical variable day along the x-axis, and so we have 4 locations because we have 4 days represented. But I could take, I have 2 categorical variables here, the day of the week and the sex of the server here. And this is what it looks like. I could swap those 2 things. This one's a lot harder to read though. Okay, well, I guess overall, maybe we'll get at kind of this disparity here. But if I removed hue day, I think this would communicate maybe perhaps an interesting feature of the data. Okay, so here if I just said sex male and female here, this gives us a sense that the numbers, the distribution of numbers over here for male is higher than it was for female over here, and so that might communicate something here. But here, if I wanted to include, say, the other variable, which was what day of the week it was, because there's 4 colors here, it's like really hard to interpret, right? I think our eyes don't like seeing these 4 colors plotted like right next to each other, and so it gets really kind of tough to see. Okay, rather than having the swarm plot, which I'm not even a huge fan of to begin with, we can do a box plot. Okay, now the thing about box plots is, if you're in like data science and you do statistics, box plots are great. Everybody kind of understands this. The general public can't read a box plot. They have no idea what a box plot. You try to explain, oh, this side is the 3rd quartile, the 75th percentile, and this is the median, and this is the 1st quartile. Like, general public doesn't understand. Okay, you can plot medians, and even like the distinction between median and average or mean is difficult for a lot of people to understand. Right? What's the difference? Why would we ever want to use the mean versus the median? Mean is affected by outliers, median's not, and that distinction is lost on a lot of people. And so certainly a box plot, concepts of box plots are kind of like don't try it. But if you're communicating to other statisticians, other data scientists, box plots are great. I think they're wonderful. And so here we get a sense of like, okay, the median values on the weekend are higher than for the weekdays, and also just more variance on the weekends as well. But there you have that. Okay, so X being on the day, so on and so forth. Let's see. Here I just swap. We're going to put total bill, the numeric variable, on X, Y on day, and just kind of turns the box plot on its side. Okay, and here you can have you can bring in another categorical variable, and you can do hue equals sex. And so what this will do is we're going to get side-by-side box plots for each day here. Okay, and so so we see this, which reveals something interesting. On the weekends, there's not much difference, or at least on Saturday, not a huge difference between male and female. But for whatever reason, during the weekdays, Thursdays and Fridays, there's quite a bit of a difference there. I don't know. Okay, and then there's something called the violin plot, which rather than doing a box plot, basically you have like a kernel density estimate. Okay, so like a smoothed out histogram rather than a box plot, and that's fine in theory, but I don't know. Not a huge fan of the way that these things look like. Okay, but that's called the violin plot. All right. Let me give you your second view quiz answer. Second view quiz answer is C. Okay. We have something called facet grids. Okay. So here, let me just kind of show this plot. So here's a distribution plot where we have, and here I'm splitting it. Okay, using this argument, rho equals sex. And so it's going to basically create a grid of plots where the top row is sex male and the second row is sex female, okay? And this gives us a little bit of distinction, and we can see, for Gen 2 penguins, as far as flipper length goes, there's quite a bit of a difference between the peak for male and female. Similarly, for chinstrap penguins, there's also, as far as where the center is for flipper length for male and female penguins, there's a difference in also a little bit there. It's a little bit tough to see. Maybe if I zoom out a little bit, it's a little bit easier to see the difference there. You can also specify row and column, okay? And so it takes a little while to generate this, but basically now I've got a grid, right? And so we can see on the Torgerson Island, there's only Adelie penguins live on the Torgerson Island, okay? And this is kind of the distribution of flipper lengths for male penguins and female penguins on Torgerson Island. Okay, on the Biscoe Island, the Gen 2 and Adelie penguins live peaceably, I guess, together. And then on the Dream Island, the Chinstrap and Adelie penguins. So Adelie penguins live on all three islands. Gen 2 is only on Biscoe, and Chinstrap only on the Dream Island. And we see kind of a difference, the difference between the density between male and female things. So this is what we call facets, where basically we've created little subgroups of our data based on these categorical variables, and we've kind of created them into little separate plots. Question?
Is each axis on both the column and the rows, are they always going to be equal?
Yeah, they're going to match. They're going to match each other. Yeah. So that's a nice feature of Seaborn, is that it's going to kind of make sure that this location over here aligns with this location over here, the 240 and the 240, because it would be really hard to compare if the top one had a different axis than the bottom one. So when you use the facet grid feature in Seaborn, it ensures that, which is really nice. Okay. You can also, so when you do something like distribution plot, displot, and you specify row and column, it does that. Here you can define a facet grid, and then you can map a particular kind of plot. So here I'm going to create a facet grid using sns.facetGrid, and I'm going to say I want to have one column to split for sex. So we're going to have one side will be male, one side will be female, and then we're going to do a histogram plot, and we're going to say for each kind of facet, each kind of different thing here, we're going to create a histogram plot where we're going to plot total bill here. And so this is what we get, okay? And here I can do, a row equals day. So we're going to get different plots, one for Thursday, Friday, Saturday, Sunday. And again, we can do map the histogram. So here I did plt.histogram, so you don't have to use Seaborn plots. So here I did plt.histogram, and this kind of plots all of these things. So you can see, so for like Friday, despite the range being smaller on Friday, okay, it kind of aligns, makes sure that all of these things have 20 and 40 at these tick marks right there. Okay. And then, you could even, again, you can specify your facet grid to account for 2 different categorical variables. So the only kind of requirement is that when you specify your categorical variables as far as the row and the column, they have to be categorical. You can't do it for a numeric one. Okay. All right, so just kind of real quickly, you can also just do like bar charts, which is like the count of a certain categorical variable. And Seaborn, to kind of distinguish itself from, I guess, your typical bar plot or something, they call it a count plot, okay? But it's basically a bar plot, and so this will do that. And here you can also specify some kind of other categorical variable to color via the data and whatnot. And then Seaborn also has the feature to kind of plot like to fit a linear model to it. Okay. Now, this one thing I should note is that when Seaborn does this, the point isn't to do linear regression. And so actually when you create a linear model plot on Seaborn, there's actually no way for you to get the intercept and the slope or do any kind of analysis. It's just kind of like you ask the computer, hey, just fit a straight line. Okay, just fit a straight line. And I just kind of want to get a glimpse of what a fitted line would look like, okay? But it's not intended for statistical analysis. So you're not going to be able to do like, okay, what's the p-value on this and what's the r-squared value? It's not intended for that. It's just kind of like, as a tool for exploration, you might want to be like, what does a straight line look like when I fit it? And that's the point of this, okay? So you have the LM plot, which is kind of like a scatter plot where it just says, all right, here is, if you throw in a straight line here, this is what you get. Yeah, question?
If you ran a linear regression model and then plot the line on a scatter plot, would it be the same?
Yes, it would be. It is the result of if you fit a linear model to it, okay? But I guess Seaborn recognizes that it wasn't designed for doing like linear model analysis, so it doesn't even want to like kind of play with it in terms of like, it's not going to give you the equation. The ability to get the equation is like tucked away from the user. And so there are packages like stats models and sklearn where you can do fit a linear model and get that information. But Seaborn's not intended for that. It's just if you wanted to fit a straight line as part of your visual exploration, you can do that. Okay, and then similarly, there you can also kind of fit a low S curve. So a low S curve. I don't know if anybody explained what a low S curve is, but it's kind of this non-parametric, locally weighted regression thing. It's kind of. Are you familiar with a moving average? So like a 7-day moving average, you kind of just take like the last 7 days and you average those values and you do something like that. The low S is kind of like that, okay? But it's not just the past 7 days. You kind of take a window of points, and with low S you can specify how big your window is, okay? But just for example, so for x equals total ability equals 20, you're kind of creating a window from say like 16 to 24, okay? And you and rather than just taking a pure average, which is just a single value, it's like fitting a linear model. It tries to fit a local regression, okay? And it's technically a weighted least squares regression, and I don't feel like getting into that, explaining what that is, but it just basically tries to fit a linear model to just this window of points. And then it fits a linear model to this, it slides the window along a little bit, fits a linear model to the next window of points, slides the window up, fits a linear model to those window of points, and then it kind of tries to join them all together into this smooth-like fashion. So you end up getting kind of like a smoothed out curve, and that's what low S does. When you do something like this, okay, you are able to get like a residual plot, all right? Just kind of exploration, just kind of see, all right, do I have heteroscedasticity? Do I have any kind of pattern in the residuals? Just kind of for basic exploration. Again, it feels, we're kind of starting to enter the region of like starting to do linear regression analysis. And again, Seaborn, its philosophy is very kind of, it will tell you this is not intended for you to do some kind of that analysis, and it will point you to a different thing. But just as part of your exploration, you can say, well, is there a difference between one category and another category? And so you can do LM-plot and specify basically groups using hue. So hue will do like what color their dots are, and you give it a categorical variable. So here we're going to do one for smokers versus non-smokers, and we can see kind of the tips for smokers versus non-smokers. And just looking at the slope, again, we'd probably need to do a real statistical analysis to see if these slopes are significantly different, but just our initial exploration seems to show that non-smokers, their kind of ratio of tips to bill increases at a steeper rate, so indicating maybe they're giving a slightly higher percentage for their tip versus for non-smokers, it's a shallower slope. But then again, this is only based on just a few dots, okay? And really, we have like these huge outliers out here, right? So you have this one smoker who had a very generous tip relative, to everyone else over here, and who knows, okay? So this is that's Seaborn. Let me go ahead and give you your last view quiz answer. Question 3 is E. That's your final view quiz answer. And again, Seaborn is for visual exploration. It's all built off of Matplotlib. Just provides kind of some nice little templates for common statistical visual exploration here. Okay, we'll end here. Have a great rest of your week. Enjoy your Friday off, and we will see you on Monday.